these are better totals, so these are the ones kind of electrochemistry, so I had put them into one document and spent a good portion of yesterday filling them in. I scanned this, it's not currently on Canvas, but it should be today.
Are we learning?
Yes, we are.
She's asking. No, I get the word.
No, I just was telling you what it was. So one more time, I found this an effective way to understand electrochemistry better. McCarthy's not in a place where she wants to understand electrochemistry today. She's in a place where she's worried about this weekend and its various deadlines. I appreciate them. I share some measure of that worry. I'm going to give you a data booklet while I'm thinking about this. Do y'all understand all this crazy math? Oh. Whoa.
Also, I don't like
Watched the video yesterday to find the PDF, CDF of puzzle. I had no idea how to do it, but I don't know how to do any. I'm not sure what this is supposed to be a note for. It's a note signed by no one that says chemistry.
Wait, she didn't sign it?
She did, I just have no idea who it is.
The lady, she's like new, I think.
At the front desk? I'm opening my data booklet to table 24. And I'm reliving the good times of last class. Now I'd like to try to make a cell out of aluminum and hydrogen. It's Friday the 13th.
Oh.
So I'm trying to make that cell. I told you the line notation was something that Margaret was going to have to read but not ever write. I have aluminum and aluminum 3 as a couple. I have hydrogen and hydrogen gas as a couple. I don't know which is the anode or the cathode. I was hoping one of y'all would tell me. Patience is a virtue. I'm not even asking you which one of these is right. I'm just telling you what I'm asking you to do is construct a cell using aluminum and hydrogen.
So you want us to draw like
And I'm saying I haven't told you which is the anode or the cathode, so you would have to use table 24 to figure that information out. I was drawing in line notation just to tell people what it was I expected of them, so as Mohab said, I'm asking you to construct a cell. And I'm just trying to write like in real shorthand, what I'm looking for is a cell that has hydrogen and aluminum as the two redox couples.
hang on, I have the This is already in space, so I feel like making notes.
I know.
Oh, okay, I'll give you a better
So
one.
I believe that we have done this. I thought this part was a review, so what's going to be new today is electrolysis. Oh, okay.
I like two of the questions are like
I would like that very much, Amarachi, yes. Which one's going to be more positive? The cathode is the positive electrode in a voltaic cell. You like that? You like that, like, clear statement of, oh shit, it's going to change? Yes. So Amarachi went straight to number 25 because she was like, I don't need numbers to answer this. I can use fingers. Aluminum is more active than hydrogen. And so she knew aluminum was going to be the anode, so she wrote it this first way. goes there, that's how we call it. Yes, goes to positive ion, goes where the electrons go, yes. It'll make more sense in an electrolytic cell why we call it a cathode. Michael Faraday decided we should call both of those the cathode. Cat ions go there. In one case, it's the cat ions in the salt bridge that we'll draw in a second. In the other case, it's going to be the cat ions in the electrolyte. Fair question. You said everything that is true.
She skips my class. She comes to you.
I didn't skip her class.
You skipped.
She skipped.
I was not present.
She was doing her hair.
She was doing that.
Actually, I woke up like
I woke up like this. My goodness.
Okay, so Amarachi was able to tell me that aluminum was more active than hydrogen, so she was able to point out that aluminum was going to be the anode, and Audrey's been honest about the charges of things. So let us finish drawing this glorious picture with all of the information that you have sold me so far. Yes. What's what? Platinum. I like the word inert there, inert metal.
Yes.
Because neither H plus nor H2 would allow me to, plug a wire in.
Yeah.
I don't know. Maybe someday in the future. Plug it into that. Dr. Hennessy?
What?
I have a question. This was also from homework. So when you're drawing the motion itself, and you have like the tube thingy of the metal or whatever, do you have to put like the ion version of it in the solution? Or like put aluminum 3+ in the solution? And then I'm asking because I couldn't remember, I just drew like the ion, but I didn't put anything in the actual solution. I didn't write it. I don't know if that makes sense, but like, in some of the examples that you showed us, it would have like a gold phase cell, and it would have like units being there, and then it would have like ions.
You have to put, like this has to be in C2 plus. Okay. So the reason that I drew this stupid line notation that none of you seem to be fans of is because of sort of Amarachi's question. It's not always obvious what the redox couple is going to be. So with iron 2, I could be trying to reduce it to iron metal, or I could be trying to oxidize it further to iron 3. How is Karthika supposed to know which reaction I have in my brain if I just say I have some iron 2 solution? It could depend on what I've hooked up to another side, but I was trying to reveal to you what I was turning what into by putting in both the before and after. Does that sentence make sense yet? Okay. So Amarachi is also realizing that over here at the anode, which I try to draw on the left-hand side to keep things as consistent as possible, oxidation is occurring. When oxidation occurs, aluminum is being turned into aluminum 3+, and electrons are starting to move toward the right-hand side to the cathode. Is that acceptable to everyone? So Amarachi said to herself, do I actually need aluminum in this solution? Does it do anything? Is the aluminum cation in the anode cell? Sophia says it does not. It's being created. But she knows that if she looks at table 24, that there is this handsome circle between the E and the volts. See how it says E, volts? And if she wants to use the every solution has to be 1 molar. So if the number that we're going to produce as the measured voltage of this cell corresponds to what's in this table, we have to have a 1 molar solution of aluminum. If we had a 0 molar solution of aluminum, we would get a different voltage. So our ability to measure the voltage using this table relies on the concentration of this and this both being 1 molar. So while the aluminum, as you said, does nothing, while I actually have an inert electrode here because the electrode does nothing at the cathode, we're just going to typically plate on it. We need those concentrations to be 1 molar in order to use a standard cell potential. because the electrons are flowing to the right, I'm gonna put a plus sign there saying that's where the electrons wanna go, this is where the electrons wanna leave from. And when the electrons hit this, what they're gonna do is they're gonna take H plus and like turn it into H2 gas. That's a really kind of crap arrow, but I didn't know what else to draw.
So, what kind of solution would you have on the right?
Hydrochloric acid, 1 mole.
How does the chlorine not mix anything up?
We are going to assume that we cannot reduce chloride further, because what would chloride be with an extra electron? So given the situation we're in, it's the best option to have. That is actually where we're headed today. I'm gonna do a demo, I'm gonna say, why am I using sulfate instead of chloride? And Brian's gonna say, because you don't want to kill us all.
So the standard electrode potential would it always have to connect to like something that has like H plus and H2? Or,
I don't think so, Mohab, but let's see if we're on the same page when I finish writing that. So when I put that standard sign, I'm gonna mean as many as 5 things. I'm not sure all of them matter, but when I put that circle there, what I mean is that if I have a solution, the concentration is 1 molar. If I have a gas, like the hydrogen gas in the standard hydrogen electrode, it's 100 kPas. I mean, I'm doing the experiment at 25 degrees Celsius and 100 kPas. I'm not sure how this is gonna matter to anyone, but I'm throwing it down. And I'm assuming that when I say this is platinum, I mean it's platinum. Or when I say this is H plus, I mean there's nothing but H plus and admittedly a counter ion. So that's what this standard means. The
okay.
standard informs the concentration or pressure of all of the ingredients.
And that is like the potential of that entire thing, of both of those connected, right?
So in the table,
Yeah.
we are given the standard reduction potential of each of the half cells separately. If we wanted to know what our battery was doing, we're gonna have to connect those two. And so we were using a formula that told us that the cell's potential was equal to the reduction potential at the cathode minus the reduction potential at the anode. I tried to convince you that what these mean are like altitudes of water, and when I'm talking about a cell potential, I'm trying to give you some information about how far my water gets to fall down.
And then using that equation, that'll give like the potential for that whole thing. Okay.
So let's do that, that's our next step. So let's find this half reaction is supposed to be the oxidation of aluminum. It's happening at the anode. Over here at the cathode, I have the reduction of H plus. So I'm looking quickly, find aluminum, it's at the top. At the cathode, I have a 0. At the anode, I have a minus 1.66. And so I would tell you that this battery is a 1.66 volt battery. We expect E to be a positive number. It implies that the reaction is spontaneous. I like the review, Mitch. I can't believe how good the rest of this is going to go.
So the one that has a higher reduction potential is always
Yes. It's what called, I don't have a word for it. It makes the standard state. I call it a circle. Sometimes you'll see a circle with a line through it, but damn it, that's not a theta, it's a different symbol. It's called stand circle in my typesetting program. You went like this, so I'm like expecting you to speak. Yes, you.
That was a mistake. I realized something.
No, I don't confuse you two. Like, it was really Sophia. If you look like she raised her hand. Okay, I'm sorry. Nikki, I'm sorry I misread your body language. I thought you were gonna ask a question. Sue me. I'm just trying to answer a question.
Does that say P, like what it says 100 kPa?
So I said the external pressure is 100 kilopascals, and this is the one where I'm not really sure how it's gonna impact anything. But the
Yeah.
implication is that I'm doing this at standard temperature and pressure, standard atmospheric temperature and pressure. So 25 degrees Celsius in a room at about 1 atmosphere. But it's key that the pressure of this is 100 kilopascals. So that's not debatable. The utility of this one is debatable. It just felt right when I was writing it. Yes?
I wanted to ask about like overall reaction. Do you have to write like the equilibrium type arrows instead of the straight line?
In a perfect world, we would probably use equilibrium type arrows. You can see that I'm not living in that perfect world yet. If we wanted to combine these two together, we would have to find the lowest common multiple of 2 and 3. It is 6. We would multiply 2 aluminums. We would multiply to get 6 H pluses. The 6 electrons would cancel. We would make 2 aluminum 3s and 3 H2s. And Amarashi wants to know if I should draw this as an equilibrium arrow. Because the reaction is spontaneous, because the hydrogen gas is presumably able to leave, I think of this reaction as a yields arrow, but she is completely right that strictly it should be equilibrium. The equilibrium constant, based on some fun calculations I did in those materials I gave you, can be as big as 10 to the 83rd. So like that is some product favored. So strictly yes, equilibrium, but actually like yields. It's because everything here is in equilibrium arrows. If they asked me to write down something from this table, I would believe them and probably write an equilibrium arrow. But I don't know that it's going to be something that's worth a mark.
And so because it's equilibrium in the table, yeah, when it has the electron concentrations, it would still be the negative Lagrange number regardless of which way the fraction is. Because I know for the equations that we're given, you know, somehow look at it from the other perspective, but it's still.
We're always flipping one equation, right? The reaction that's occurring at the anode is always going the other way, which is why I believe they're showing you as two-way arrows. So we are always flipping that one and accounting for the sign in our formula with that negative sign. So we are always using the numbers that are in the table and using this formula where it automatically is accounting for the fact that anode is oxidation.
Oh, it's not, okay.
So, point out another thing, half of these reactions are going in the backwards direction. So that's why I believe that they're using the two-way arrow, not so much to convey equilibrium thoughts, because again, the equilibrium strongly favors, in that case, the product side. But just to say that we know that we're actually going to oxidize lithium, we're not going to reduce lithium 1. You ready to move on? It's been such a glorious day so far. Okay. So I think what I want to do is talk about non-spontaneous cells. And so, no, let's go for it. We're going to try to separate the world into voltaic and electrolytic cells. Some of you have noticed that voltaic are sometimes referred to as galvanic. You might see that word in your travels. They're synonyms of each other. But over here, electrolytic comes from the notion of using electricity to break something down. So this is going to be the process, say, of taking magnesium chloride and decomposing it into its elements, magnesium and chlorine. So that is going to be sort of the number one use of electrolytic cells. Magnesium is the third most common element in seawater. There's lots of magnesium ions there. We use the magnesium in seawater to generate magnesium metal electrochemically, and that's how we build fireworks, and that's how we build aeroplanes and other really light things. Sodium, the only way to make it is through electrolysis. On Earth, there is no reserve of sodium metal. It's far too active of a metal to exist in its metallic form. So it always exists as an ion, and we need to do something to reduce it. And so this is that process. Some differences between voltaic and electrolytic cells that hopefully you will notice is that voltaic cells are spontaneous, while electrolytic cells are not. What that's going to mean is that we are going to have to provide electrical energy. We're going to use our own battery to make chemical potential energy. To put the electron back on sodium, or to put the electrons back on magnesium. Whereas here in a voltaic cell, we were using the relatively high chemical potential energy of the electrons on zinc to produce electrical energy as they traveled to some copper-2 ions somewhere in the world to make copper metal. So we were taking, in the voltaic cells, high energy electrons and allowing them to move to a low energy space and trying to harvest or harness that energy. Now we're going to take low energy electrons and try to raise them up. In a voltaic cell, you will notice that I typically have two cells, two compartments, connected by a salt bridge. So let's all fix our middle picture. Throwing a salt bridge in that middle picture so no one thinks less of themselves when they look at the picture. We just got so mired in other discussions that we didn't get through. I apologize. In electrolytic cells, typically there's going to be one compartment, and consequently there will be no need for a salt bridge. It's just going to be filled with an electrolyte, something that can conduct electricity. The final difference that I typically make in this list is one that I think Audrey was alluding to a little bit ago. She said that in a voltaic cell, the anode is negative and the cathode is positive. To keep you guys on your toes, it is the opposite in an electrolytic cell. I remember that with a silly acronym. The acronym I use is PANIC, positive anode, negative cathode. When I see an electrolytic cell, I panic. They are not my favorite. So again, to write down what this means, this is going to mean that the anode is positive and the cathode is negative. I will try to defend that in my picture, but I know that that's a very common question in the multiple choice to understand that change in sign of the anode and the cathode. So to draw your first electrolytic cell, I'm going to use magnesium chloride. I'm going to draw a cell that's slightly too simple to actually do this. Like, if you want to build a magnesium chloride cell, Sophia, don't use this model. There's a reasonable model actually in the notes, but I'm not feeling it right now. One more time, I have two electrodes, and I'm going to make the anode on the left and the cathode on the right. The anode is always where oxidation will occur, and the cathode is always where reduction will occur. I'm going to put these into some magnesium chloride that is molten. I use the word molten there to convey that it's hot. It is a liquid version of an ionic solid. I have melted a salt. We're sitting around 600 Celsius. Magnesium chloride has a relatively low boiling point, but it's a lot. So liquid magnesium chloride is not something you would expect to see very often. And I'm going to put a battery. And what batteries do is they pump electrons. And my battery is going to pump electrons from left to right. There are two ways of saying the next sentence. My preferred way of saying it is that I needed this battery because I am forcing the electrons to go in the direction they don't want to go. So in my head, that's why this is negative. It's not spontaneous. That's why I needed the battery to convince it to go to the minus side. If that is not appealing to you, you could say that you are pumping electrons to the right, so of course it takes on a minus charge. Both of those, they're the same. But to me, this is conveying the non-spontaneous nature. The electrons are flowing in the non-reasonable direction. But again, what Audrey was saying was, how does it make sense how the cations and anions are flowing over there? It's going to make great sense here. If I have an electrode with a negative charge, who's going to show up? Magnesium or fluoride? Hopefully everyone is saying magnesium. The cations are going to flow to the cathode. So this time it's actually the cations which are going to be reduced, and these cations are going to be reduced to magnesium metal. Magnesium metal has a lower boiling point than magnesium chloride, and so this would be liquid magnesium if anyone were paying attention. At the other electrode, which has a positive charge, what we will find is that the anions flow to the anode, and they get oxidized there to make chlorine gas. Debated a lot on that one half. You don't have to write it if you don't like it. It looks a little bit more balanced to me. At the anode, the chemical reaction that is taking place is oxidation. At the cathode, the chemical reaction that is taking place is reduction. If we found the least common multiple of these two things, 2 and 1, it would be 2, and we would add these equations together to say that magnesium chloride is being broken or lysed to make magnesium and chlorine. How much cell potential do you think we need in that battery? Well, let's find in our data booklet some information about the reduction of magnesium and chloride. So magnesium, the reduction potential is negative 2.37 volts. Chlorine's reduction potential is positive 1.36 volts. I have underlined the word reduction because Quinn's going to remind me in a moment that this is an oxidation reaction. Everything in my table is reduction, so I just make a note. The overall cell potential here is supposed to be equal to the reduction potential at the cathode minus the reduction potential at the anode. And it is a negative number. Emma says it's negative. That means this reaction is not spontaneous. That means we're taking electrons down here and trying to move them up here. So we need to make sure that the battery that is pushing on them is bigger than 3.73 volts. Otherwise, the electrons won't flow. Everything I'm assuming is standard conditions, so I should have zeros on everything. I tried pretty hard to put them down. The negative at the end is what's telling me that this is not spontaneous, and so that's why I know that the battery that I've attached to it has to be bigger than that. So I imagine a marble, and the marble's got to go up a hill. The only way I can get a marble to go up a hill is if I drop it from a bigger one. right? So if I drop the marble over here, it will have enough energy to surmount this hill. But if I just start with the marble at the bottom, it's just gonna sit there and be like, whatever, I'm gonna sit here forever. If you enjoy the stuff that I gave you, you're gonna find that the production of a gas costs a little bit of extra energy. It's a little bit hard to make those bubbles nucleate. And so you probably need something that's closer to 4.5 volts. So if you, like Raimi, did an experiment with electrochemistry, you might want to look at overvoltage. If you, like Reckon, did an experiment with electrochemistry, you might enjoy reading about the derivation of the Nernst equation and how we handle things when they're not 1 molar. We are going to make some comments about if it would be bigger or smaller, but the actual formulas are hard. And so I gave them to you because they help me understand, like they make connections to topic 16 and topic 17 and topic 15. And I feel better when things mesh together. Emma feels better when she's done with her homework and she gets good marks on IB scores. Right? And that's fine. She does great on everything. But like it makes sense to me to have this connection, so I gave it to you, and I'm not asking you to do anything with it. So if you're like, Nernst equation not in my syllabus, flip the page. I am not crying myself to sleep. It's not in your syllabus. I'm not trying to mislead you. It just helps me to make some things make sense later on. I would say about 20%, 25% of you did some form of electrochemistry. So I felt like it was okay to like include a little bit more juju on the electrochemistry. So it was a bit self-serving. Me. This part of electrochemistry, short of calculating the number 3.73, is all in chapter 9.2, meaning it is SL level. If you want to rev this up, what you're going to do is say the world is a fantastically interesting place, but molten magnesium chloride is rarely what I have. What I have is aqueous solutions of stuff. And so what I'm curious about is what would happen if I had 2 inert electrodes connected by a battery such that this one was negatively charged and this one was positively charged, and I put in a solution of magnesium chloride aqueous. Well, now it's going to be interesting because I have 2 things that have kind of negative charges. The first thing I have that has a negative charge is the chloride ions. So chloride could flow to the anode, which has a positive charge, I learned, and chloride could be oxidized to make chlorine gas as well as an electron. But water is also a polar molecule, and if I thought about the oxidation states of the hydrogen and the oxygen, I might recall that oxygen has an oxidation state of -2. And so maybe instead of oxidizing the chloride, it would be possible to oxidize the oxygen in water to make O2 and 2 H pluses and 2 electrons and a 1/2 because I math hard sometimes. How would I choose which of these reactions was more likely? I'm going to do the other ones and then you're going to tell me. At the other electrode, before Audrey tells us all how to do it, we could reduce the positive magnesium, which is going to flow to that negatively charged electrode and make magnesium metal. Or we could take the positive part of water. Positive part of water is the hydrogens. And we could add 2 electrons to them, and we could make some OH minuses and some hydrogen gases. And I think I balanced it. How would we figure out which one of these reactions were right? These reactions are written in table 24, so I'm sitting here trying to balance them because I'm too lazy to get my book out, but they're free. Now Audrey's going to tell me, how do I select? Which one is more reactive? Kind of. What does that mean? How do I know what reactive is? Active typically has to do with oxidation. So perhaps I could do it in terms of the properties of what I'm looking at. So what do you think is easier to steal an electron from? So maybe if I had chloride and bromide, Audrey could convince me that it's easier to remove an electron from bromide because it's bigger. Or maybe if I had sodium plus and magnesium 2 plus, she could convince me it's easier to give an electron to magnesium because it's smaller and more charged. So maybe I can go back to periodic trends and do something, but I don't know how to do that between like things that aren't in the table. So she's not wrong. If I know something about the material, she's got to be right. But I really like water here, and so I'm gonna ask you a dumb question. Imagine that I block this sink up and I turn the water on. Where does the water spill? It spills right here, right? It floods over the. How about if I hold my hands here very optimistically? Will it ever be like, yo, I feel aspirational today. I'm gonna jump out over her hand and overachieve. Water always does the easiest thing it can, and electrons are just as flippin' lazy. Electrons will find the smallest hill that they can climb. So I'm back in table 24, and I'm gonna do what Audrey said. I'm just gonna do it. With my fingers, there we go. Water and magnesium. Oh, magnesium is really hard. Okay, on my right hand, your left, I don't know how to do this. I have the two things that could happen at the anode. At the lower part, 3 lines from the bottom, I have chlorine, and above it, 2 lines, I have water. You feel that? And on the right-hand side, I have water with my middle finger, and I have the magnesium's up here with my index finger. What is the smallest hill I can climb? It's these two. I'm going to do the easiest process for both. And so what I'm going to find is that I will preferentially make oxygen at the anode, and I will preferentially make hydrogen at the cathode, because these are the 2 things that are the easiest to do. So what I have actually done here is not electrolyzed magnesium chloride at all. I have electrolyzed water. Why did I need the magnesium chloride? As if I just put water in there, I would not get these results. I need something that can conduct electricity. I need ions that can flow, and so I need that electrolyte. I need something like the salt bridge. So I believe that children are the future.
God help us all.
Did you guys not know that song? Children of the future, I don't know.
But what's the rest of it though?
Okay. I don't know, having a moment. I feel like it's gonna be Whitney Houston. I'm looking in the very last set. So the last set is called ALE 27. It's gonna be the last 7 pages, and I am on page 2 of the last 7 pages.
The last.
I mean, Quinn can just cross out the middle where they're telling about the Nernst equation, and his experiment has nothing at all to do with the Nernst equation, and he's like, this is great, but I am 100% sure it's not on my exam, it's not on my IA, and you know, I have other hobbies. So, felt like if I started skipping things, people are gonna be like, where's 25? And if I didn't, they're gonna be like, what did she give me 25? So, you know, I had to make a choice. So I'd like you to consider this cell of sodium sulfate. You see it, number 5? I would like you to try to do problem number 5. Not just problem number 5. You guys were in here yesterday, you moved my things. Students suck.
And how? Why do you need more girls in computer science? Well, why do you need more? Well, why do you need more?
It's great because of, I mean, Caroline's there, but she's gonna argue with Alex and so whole time topics and lots of Sorry, every base soccer games. And we already watched those last summer games, so. It sucks.
It says page 2 of 7 at the
No,
bottom.
you need to be here yesterday when nothing worked.
Sorry. Oh yeah. That's the last 7 pages.
Sitting here with a scalpel shaving these things down, they still are gonna leak comically. But I try not to lose any fingers screaming, okay, you did number 5, now change that electrode to copper. And they're just looking at me like I'm mentally. I was trying so hard to pay attention, but I was also trying to get this set up.
It's electrolysis.
Andre's like, are we gonna do any demos? Didn't want to set it up today. Shut up, Andre. I've said that a lot in my life.
What's that mean? What did you
Yeah, oxidized caffeine.
That's good.
The anode is like the oxidized
He just made me feel poorly, so I put on my calendar that you guys were gonna do reactivity series experiment today. And then I was like, who's gonna set that up? I don't know that I want to be the person who sets it, so I just like pushed it to next time. So he made me feel poorly about myself.
Something small as hell.
Sorry, no, it is the anode.
Are you looking at like the
Just the anode.
What? What's the anode?
Part where I think we all died.
In the small scale.
Everyone's a critic.
But nobody wants
Small
that.
scale? I don't understand this.
Is it Boulder?
Oh.
I'll make sure nothing explodes.
I say Boulder.
Yeah, but we know
Why?
Because it gives the standard reduction potential and the negative of that is the oxidation potential, right?
Yeah.
So that's higher than
the oxidation
sulfur.
potential that is higher means there's less.
It's less negative.
And does that mean there's like less work?
But I think so. It makes because like with the activity series, the bigger the difference, the more electricity flows. So like probably makes it easier. Maybe the charge of the voltage of the battery is higher. We don't need to do the weird thing. We just have this. All we need is this. This is negative 1.23 for if it's oxidation.
Anode intake, so the anode is the one that has the more negative electrical charge. So is it small for
For electrolytic ones, are like, you know how she made the anode positive?
Yeah, anode. So now it's
But the cathode is where the electrons are going to become more negative.
They're
Right?
asking what species make oxidized graphene. Then you oxidize
sodium sulfate in water.
Don't know the
I added a little bit of bromocresol green. The water we have is, a little bit on the basic side of bromocresol green. It's green at about 6. You would expect water to be 7. So that's why it's not as green as you might like. But hopefully, thanks for the paper towel, you're noticing that this side is turning a different color than that side. If you're not noticing it, I can put a white sheet behind it, and hopefully you can see this side is turning a little bit yellow, and this side is turning a little bit, or staying a little bit blue.
Blue-white,
What?
like frosty.
Well, it's because there's gas bubbling through it that it looks frosty.
Frosty.
So you can see the gas bubbling through it, slowly but surely. It's starting to collect up here. So the water level is actually here now, and this space is filled with gas. This water level is somewhat higher, it's only there. Why do you think we're making gas faster on one side than the other? It's not gonna, I'm gonna unplug it before I start touching the wet parts, but it is not gonna blow up. Nice. Here, you can have my spot. No, if you don't want, I'll hug anybody. You're not. Yes, I'm asking why it's making gas faster on one side than the other. Water and sodium sulfate and some indicator to make it look pretty.
One side's making O2.
That's, I think the problem number 5 was sodium sulfate and water. So I did sodium sulfate and water.
Sodium sulfate water doesn't.
I presume so.
In the what's it called? The oxidation or whatever of water, it produces O2 gas. Is that
Okay, so one side is O2. That's the side we're oxidizing. I agree. Can we decide which side is O2?
the white one?
The yellow one? Oh,
It's a white one.
because you're making more gas?
Yeah.
Wouldn't I make H2 faster than I made O2?
Yeah.
Because I would make 2 H's for every 1 O.
Yeah.
Let's see if it makes sense with the colors of things. If bromocresol green is in table 18 of your data booklet, maybe we can figure out which side's acidic and which side's basic. Feel like that reach for table 18 was real, right? I don't know, I made it up.
And it's kind of dripping on the floor. Is that a hazard?
Table 18 ain't it, is what she's saying? Oh, not even close to it.
Less.
How about 22? 22.
This one's more bubbly.
So bromocresol green is yellow in acid and blue in base.
Yeah.
Interesting.
That
Not what you'd
side's
expect.
basic, that side's
So that side's basic, that side's acidic. So which side, can we look at this and make a decision?
what?
You're telling me this is the blue side?
The basic?
Yeah.
It's not what we expected. And this is the yellow side?
Because I thought, don't hydrogens make something more basic?
What?
Don't hydrogens make something more basic?
H pluses? They make it more acidic.
More acidic?
Why do I feel unhappy?
Because this is
Because water's supposed
It's
to
so many reasons. Why right this moment?
Is it because water's supposed to be neutral?
Is it was supposed to be neutral?
I would have expected to make the hydrogen gas faster. What is the hydrogen gas having to travel through? It's traveling through a big tube of water, and so we might have to wonder about which is more soluble in water, hydrogen or oxygen. We might also have to wonder about the fact that with the leak, which one of the gases is more likely to be affected by the fact that it's certainly not gas tight or water tight for that matter at the bottom. So my expectation would have been that the blue side had hydrogen gas and that the yellow side had oxygen gas. I don't know how I feel.
Is this that, or is this the one from there?
It doesn't actually change anything. The magnesium chloride is unrelated. The sodium sulfate is also not being oxidized or reduced. It's the water in both cases. I just gave you your own example to struggle with, but it's the same result.
I'm confused.
Dripping on the floor, is that bad? I don't know.
It's dripping on the floor.
Yeah, there's a
It's not.
Amazing. I am surprised that this is forming faster than this.
Oh.
My expectation would be that the hydrogen is forming twice as fast as the oxygen. Now this one has a lot of big bubbles throughout it. I don't see as many big bubbles throughout it, but this one just appears to be going faster. If it appears to be going faster, then I would expect that it's the hydrogen side. This is the hydrogen side. I'm just dumb. I don't know.
It was upsetting because she thought this was the other thing.
This is the hydrogen side, isn't it?
The blue
No.
side is the hydrogen side. Everything is perfect.
Huh?
I'm in a perfect world. I was not in a perfect world, but I'm good now. I can explain it again. I'll be good.
Wait, I'm just gonna go back.
So looking at these two things, what I noticed is the gas is now down to like almost 1 kilogram. Whereas here the gas hasn't actually started to hit. I am making gas faster on this side. I see that in the bubbles as well. This is the side that appears to be basic, it's blue. The side that is basic and blue is the hydrogen side. Again, it's the side I expect should be made twice as fast, and that's what I'm seeing. I thought what we were seeing is that the gas amounts weren't consistent with what we thought, and so I thought it was because hydrogen was more soluble in water. But we are not seeing that, though it may be true. We get rid of this unhappy face because we're happy. How would... I know. The number of electrons being oxidized and reduced is equal. So if I were to add these two equations together right now, I would say that 3 waters are coming together to make H2, 1/2 O2, and some H plus and some OH minus. And so what I'm trying to point out to you is that I expected this 2-to-1 or 1-to-1/2 ratio, and we are seeing it. I just had it backwards because I got confused, but it wasn't backwards. It's all good. And again, another way that I was trying to help you visualize which side was which, aside from having twice as much gas here as there, was by taking advantage of the fact that this side is making acid, so turning our bromocresol green yellow, while this side is making base, turning our bromocresol green even bluer. Now, I had given you the example of magnesium chloride, but asked you to think about the example of sodium sulfate. It is my expectation that what you determined was that as magnesium is more difficult to reduce, so too is sodium. The number of volts required to reduce sodium is very high. It's one of the most active metals, and consequently, it's at the top of the list, meaning I have to push the electrons up very high to achieve this change. The electrons have to have a lot of energy in order to put them on that sodium. So energy and volts are going to be different because volts are going to tell you something about the distance in altitude, for lack of a better word, between the oxidation and the reduction, or that the electrons have to travel, whereas energy is going to tell me something about how much water is flowing. So the water flowing here is the electrons. So I believe that last time we saw each other, we related voltage to energy using the Gibbs free energy. And so I believe that we wrote down this relationship. And so I would tell you that if I knew the cell potential, then I could tell you how much work I could do, or how much work I would have to do in the case of electrolytic cells to make this happen. So I'm saying that on occasion we need to be careful with the distinction between energy, and cell potential, because it includes the number of electrons that are moving, the N. So I just want to make it clear that N matters sometimes. Think about it as potential energy, you'll be fine. Just recognize that if you're calculating free energy, you have to worry about how many electrons are flowing. If you're willing to look at those as just the potential energy term, I think that we will be good. And we want the lowest potential energy for the reduction reaction, excuse me, and the highest for the oxidation reaction. Okay. You want the hard part now? It's not that hard. You ready for more?
Wait, so this isn't the hard part?
No?
Okay.
That's pretty straightforward.
Yeah.
Oh, do you have like a so originally it was like you would take the higher number.
So this is the easiest thing to oxidize, but I'm trying to reduce it, so it is the hardest thing to reduce. That is the sort of distinction. Yeah.
I still.
So I wondered if we imagined another system. What if we imagined a system in which we had copper sulfate? And aqueous. Over here I have the anode, over here I have the cathode. What are some anions or some negatively charged things that might go to the anode to be oxidized? What are my options? Anode. I'm a left to right kind of gal.
Be oxidized.
I know water's going to go to oxygen because I have like a deep and abiding understanding of the H pluses become H2s and the O2 minuses become O2s. I know this is the most common set, so I'm not trying to balance this equation again. You saw it was in table 24. It's free. Sulfate's actually not even in this table. I know it was in the work you just did. Oh, it is here. Never mind. It's here. It's here. I think it's a different reaction that's here. So you had sulfate being oxidized. I have sulfate being reduced in this table. Over here at the anode, what am I trying to do to sulfate? I'm trying to oxidize it. So is this equation even relevant? No, because I don't have those ingredients. So that's why I'm going to fail on that. I knew I could fail on that. So you guys have the number because you have some extraneous information. If you were sitting in an IB exam, sulfate doesn't even make the table because my expectation is that you can't oxidize sulfur. It's apparently wrong, but sulfur is in the oxidation state +6 here. Sulfur has 6 valence electrons. The fact that we're going to try to get a 7th valence electron out of here is crazy to me. Just don't think I can. So I believe that on this side, the most obvious thing for us to oxidize would be water.
Why did we abandon the again?
It depends on what resources you're looking at. So if you're looking at this resource, which is the one you have in the exam with you, we don't even have a reaction that considers the oxidation of sulfate.
Isn't there?
That's the reduction of sulfate,
Oh yeah.
which we wouldn't do
Yeah,
at the anode. So I would just throw it away. So in 19.1, when you're learning this shitty HL part of electrolysis, you're supposed to just know that sulfate doesn't do anything. Like it's just presented to you like it's obvious.
So sulfate cannot.
Sulfate will not be oxidized in IV chemistry.
Okay.
Done.
So it's at +6.
It's already at +6, so where do the electrons come from? Doesn't quite make sense. They have to come from the oxygen somehow. But over here, what are some things that I could reduce? How would I choose between those, among those? Here's copper. Here's water. I'm gonna do the copper. So this is a means of actually plating out copper. So if you do copper sulfate in the presence of inert electrodes, the expectation is that you will make copper at the cathode and you will make oxygen at the anode. So if you watch Chris do his electrolysis experiment, this is what he saw. No, you guys didn't watch him, but I watched him because I'm in both classes. So he saw bubbles at one electrode. He used graphite electrodes. But Ramey did not use graphite electrodes. Ramey did things differently. Ramey was like, yo, I'm gonna use copper. What does this change? Is there any new reaction I can do because Ramey decided to use a copper electrode instead of a platinum or inert graphite, in the case of Chris, electrode? The what? Someone's gonna have to translate. Oh, the electrode might wear away. Whew, sorry. What Audrey was saying in my language was the copper can be oxidized. She's totally right that the electrode might wear away. And I just did not understand the words, sorry. What is the redox potential? What is the cell potential of Ramey's experiment?
Of the whole thing.
The whole thing. So Ramey figured out that she had one electrode wearing away at the anode. She had another mesh electrode where copper was depositing. What is the cell potential for this? It is 0. We are doing and undoing the same thing. We are taking 2 electrons from copper and putting them back on copper. The cell potential is 0 here. This process is typically used for either electrofining or electroplating. Electrofining is the process of purifying copper or another metal you want. At the anode, the one that's going to be eaten away, we're going to have copper that's not very clean. And as we oxidize it, what we're going to find is that any impurities, especially those that do not conduct electricity, will just fall to the bottom of our pot. So if we have like some sulfur in that copper ore, the sulfur would just fall right down. But copper would be plated over here in its pure form. And so we would be able to make like some nice copper bars. So if you have silver in your house, I used to get it for birthdays when I was very little, it will say like electrofined. And what it means is that they made something that was a very pure silver. I don't know why, a gift. Actually I do. My aunt and uncle, they actually reclaimed photography materials and took the silver out of black and white photography materials and reduced it down to silver metal. That was like their profession for a while. Seems like a really crappy and smelly profession, but yes, that was their profession. It was like a 1 ounce piece, like it was a $15 piece of silver that would say happy birthday stamped on it.
50 or 15?
1.5.
1.5? Does it matter? I was like,
She's trying to Christ, like she's trying to case my house now. How much silver did you get? How many birthdays did you have while they were still working in this industry? Is it worth it? I also have a Krugerrand.
Krugerrand?
Krugerrand?
What's a Krugerrand?
It's like a gold coin.
How much is
1 ounce. It's my mother's 1 ounce gold coin. See, in South Africa they do lots of terrible things. There's like diamonds, there's gold. It's all a terrible industry, but my mama got a Krugerrand.
Nah.
I like this picture, and you're certainly going to want this one in your notes. You get silver. All of my life, I've wanted a silver-plated trident because I can't draw a spoon or a fork. I have found over years of trying to draw this picture. So here is the trident that I'm trying to plate. You can plate whatever you want. On the left-hand side, you have a pure sample of a metal like silver. On the right-hand side, you have something you're trying to cover up. And what you will do through this cell is you will take silver and you will oxidize it into silver ions at the anode. At the cathode, you will take silver cations and you will deposit them onto the surface of said trident to make a beautiful silver-plated placed setting. This has an aqueous solution of silver nitrate. What's kind of curious about this is that every time an atom of silver becomes silver plus, an ion of silver plus becomes silver, so this solution never changes. It always has a constant concentration, so you can use it indefinitely. When I was working at Rice, we actually made nickel nanoparticles this way. We electroplated nickel into a filter. And so we got nickel in the pores of the filter, so they were really, really tiny pores. And then we dissolved the filter, and so we had nickel nanoparticles. Not really sure what we did with them. We looked at them. You put it in a new piece of silver. So you're really interested in that fancy place setting or whatever you silver plate in your life. I don't silver plate a whole lot. But this is how it's done. It's just a simple electrolysis reaction. What's fun here is that we haven't done stoichiometry all class today, and Sophia really likes it when I do stoichiometry, and so she wanted to remember, look at the deer in headlights. She's talking about me again. So what she found out is that Brecken used a current of 10 amps for a time of 2 days to plate silver out onto this trident. And the question is, how many grams of silver did he manage to plate onto the trident? An amp is one of the 7 fundamental SI units, because someone hates both of us, Audrey, and it stands for ampere, and it means coulomb per second. Oh, I like this. So coulomb has something to do with charge, and so I'm watching you how much charge passes per unit time. So that's what a current is. It's electrons flowing per unit time. You might also know that we used F a few times recently. F has the numerical value 96,485, and it is the charge of 1 mole of electrons. So it's a handy dandy conversion factor for these problems.
What's the difference between an amp and a volt? We can
Everything.
figure that out. Yeah, but
Like V equals IR is what the physicists will tell you, right?
what is amp?
And so like this is the voltage part, this is like how much I've got to push the electrons, and this is how hard like how fast they're flowing. This current, the flow of the electrons.
Is volts?
This is volts, this is electric
The
potential.
R is the R resistance.
Yes.
Yes, you know.
And then what's
It is. How is this again this year?
amps?
It's how fast the electrons are moving.
So the I is the
Current, I amps, yes.
Oh, so V is just the F, but with the resistance.
Thought that meant something to you.
That helped. A lot.
Okay, this is a dimensional analysis problem because Emma knows that she may or may not have to do this once on a test, and she really doesn't want to memorize 50 formulas or something that she may or may not have to do once. So she's going to say to herself, hey self, what was the given? And the given is how long Brecken was willing to pass this current. They will always give it to you in an uncomfortable unit of time, like days. It could be hours. But she knows that she needs it in seconds because she knows that amps have something to do with seconds. So she's going to say a day is 24 hours, and an hour is 3,600 seconds. And she's going to feel better about the world because at least she now knows the amount of time that Brecken's spent doing this reaction. So this is time. Then Elizabeth's gonna say, well, you passed the current, and the current is how many charges went per unit time. So the product of these two things would have units of coulomb. It is a total charge. It is the amount of electronness that passed. But in chemistry, we are rarely interested in coulombs. We are interested in things that are more practical because we gotta get to grams of something. So I know I need some moles. And so what I'm gonna do is I'm gonna use Faraday's constant to relate the amount of charge to the number of moles. So I'm gonna take these coulombs and I'm gonna multiply by, there are 96,485 coulombs in 1 mole of electrons. And so now what we have determined is not what charge went through this circuit, but instead we have figured out how many electrons traveled through this circuit. And that magical step is gonna allow us to say that silver takes 1 electron to go from its ion to its metal. So for every mole of electrons, I would make a mole of silver, and of course silver weighs 107.9 grams. Yeah, so it's the time times the 10 divided by Faraday's constant times the molar mass. So when Karthika's like, silver's nice, but I'm looking for something a little bit nicer for the family, she's like, let's talk gold. Gold's most common oxidation state is +3. The places where it's gonna matter that she chose a different metal are gonna be right here. That's the one you're gonna forget. It takes 3 electrons to completely reduce gold ions to gold metal, and then I don't know the molar mass of gold because we don't talk about it too much. It's 197, I think. But that's easy. You would all look up the molar mass of anything you had. So you wouldn't forget that piece. I'm not worried about that piece. But this piece, where we are trying to figure out how many electrons it takes to fully reduce a metal down, is a piece where I think that sometimes people make mistakes. Depending on the time, we'll do, one of 2 things. Always too late. What? 10 minutes. So why don't we do a practice one of these? And I'll tell you my sodium chloride story another day, I guess. So you're still going to be in that very last set of stuff. That was the one that was out of 7 pages. And you're not going to be looking at question number 5 because that's right out. You're going to be looking after that. You're going to be looking at like the last page. Like very last page. And you're going to try problem number 13. And if you're super duper confused, you can look for, they wrote out how to do it on the previous page. So you're trying to do problem 13 on the very last page of this glorious set of information. That's me. I don't know. Emma got an answer because she's a better human than I am. She got an answer that is smaller than the one I expect, so I'm trying to find a calculator. So you took 48.
Dude, I love I don't know if it's a silver screen.
Yeah, definitely. They've only been in
I got 193. I'll do it again because I feel like I didn't do hard. I got 1900.
That's not
Okay. Good multiply
You had done
So Emma and I did that calculation, we both got about 1,900 grams, if you ever want to look at it again. If you don't, we also got 1,900 grams.
If you want to get rid of this girl,
But you're doing one about zinc.
I see raccoons in
what are you?
It has the advantage that I did it yesterday, so I won't look it up. So Chris wants to know likeliness that this was on the exam. I've certainly seen it on an exam before. Sophie is undoubtedly praying for it because she loves stoichiometry. She knows these problems are straightforward.
Your brain.
Are you not Sophia?
I'm praying all the time in this class. So.
Yes, Summer?
Where did you send silver S from?
I told you that the amps in the experiment that we pretend did was 10. And so an amp is just defined as a coulomb per second.
So for the frequency, that would be the amp thing given.
Yes. The 0.755.
Is there a thing with like, the zinc ion is a limiting?
Oh, yeah, it's definitely limiting. Like all of the electrons are going to zinc. Because we were taking zinc from one electrode and plating it onto this box.
But what if like it keeps happening the number of electrons in the zinc? How does the zinc better?
Like you're gonna use up all the electrons on zinc. We presumably have like a inexhaustible source of zinc. We use this to like plate the bones. So you're not worried about running a real like uranium experiment. Like you're worried about it. But in this, like we actually put like giant plates of zinc on bones to try to convert to make the zinc get oxidized instead of the bones. Because I knew the charge on wood was 3+, so I just wrote that down like I knew.
Yeah. I know.
It's really working in tree. It didn't leak so much, it looked like professional. It's called a Hoffman apparatus. I had one growing up.
Yeah. I love the notes on it. That's what it looks like.
Ask me a harder question.
It's the notes from Lost Spot.
He worked at Hughes Aircraft Company doing optics.
Because it was kind of convenient.
He
Because
was
I
like there
started
for the
here
birth of computers.
just writing some stuff. And
So
then
it was like learning how to do scientific computing. But in the lens of optics for like
Oh, okay.
very bottom, and I expect to get it.
So an amp is a C per second.
So it's a constant.
That's what we do.
So that would be C's per second. So I never, I mean, I understand that the problem's always gonna give me amps, but I always write just C's per second. Amps aren't a very chemistry unit, but coulombs are something I didn't understand on the line. I just go straight to C's. So 0.75 C's, and then I think the number that you have next is not amps, but C's. And now I think you're perfect. Yes. Two little electrons for one mole of zinc.
Probably get words from.
Okay, that's true. There's a mystery 3 that we forgot about.
So it's gonna take 2 electrons to make this zinc into zinc metal. Which is 65. Yes.
For that one, where
Yes.
did the 3 mole electrons?
Because gold had a 3+ charge, it would take 3 moles of electrons to make it gold. Silver had a +1 charge, so it would take 1 mole. Zinc, in your problem, has a 2+ charge, so it'll take 2 moles. If If you didn't know, zinc had a 2+ charge. There is the table of oxidation states, and zinc will have the +2. It's the only one it has. So there's a place to be like, oh, I don't know this. I could find it. Or it's like, if I had an extra 10 minutes, that would be marvelous, but.
No, that's
Okay.
I'm like barely. That's what I have. I just put 65 as the goal. Because I got 43.9.
I just put the interest thing.
What if you electroplated a human?
So the only thing I didn't tell you, and the thing that I think that Mohab will think is hard that I didn't get to, I just want to say it out loud and then we'll talk about it for real next time, is I want you to notice that water and chloride are really close to each other. One is 1.23, the other one's 1.36. And those two values are kind of close. They're within like 0.1 of a volt. None of us have a really good idea of what 0.1 of a volt is, but if you compare that difference to the difference between water and sodium, it's going to be closer to 2 volts. So it's like 20 times closer. So they're considered to be nearby. Unfortunately, this table is written all in terms of things having a concentration of 1 molar. If I change the concentration by using brackish water, briny water, super concentrated chloride solutions of water, what's going to happen is I can change these numbers a little bit. If you want to do the glorious mathematics, you can use the Nernst equation to prove it, but we're going to like kind of talk ourselves through Le Chatelier's principle as a nice review. Think about why if I put salt in here, I could have made chlorine gas instead of oxygen. 44.2. Bye. So if you know how many moles of electrons, I know that zinc is going to require 2 moles of electrons. So I'm going to have half this number of moles of zinc. Every 1 mole of zinc requires 2 moles of oxygen. So if I took this and divided by 2, I would have 2 moles of zinc. And multiply by the mole